let's get down to what I want to talk about next. We have been talking last time about the product rule and the quotient rule. There is one more kind of named rule that goes along with the product rule and the quotient rule. And the product rule, of course, is how you take the derivative of a product. The quotient rule is the derivative of a quotient, that is a fraction. The third of the rules is about the derivative of what we call a composition. A composition. This is when you combine functions not by multiplying them or dividing them, but by actually sticking one function inside of another function. That's what composition means in this context. So what that would look like is something like the derivative of, how about x squared plus 1 to the power 100. This is a function stuck inside of another function, and that's called a composition. The inside is x squared plus 1, and then the outside is that 100 power, all right? So a composition means one thing inside another thing. And in this case, so with like a quotient has the top and the bottom, the product has the first thing and the second thing. The composition has the inside and the outside. So when you're doing this rule, you always want to think in terms of the inside and the outside. And in this example here, the inside is x squared plus 1, and outside is the 100th power. All right? And the rule for this involves some combination of the derivatives on the insides and the derivatives on the outsides and that kind of a thing. So it's similar in spirit to the product rule, which is about the first thing and the second thing, but it's about the inside and the outside, and the rule is different when you write it. And it has a weird name for some reason. I'm not sure why it's called this, but this is called the chain rule. And this is the rule for the derivative of a composition. I will just write it like this. The derivative of... So the way a composition looks is it has one function with another function stuck inside of it, right? This is generally what a composition looks like. It has f is the outer function in this case, and g is the inside. This is not f times g. This means you stick g inside of f. You're not multiplying them or dividing them or anything. It's something else. It's a composition, all right? And the rule for this one is actually, the proof of this is quite complicated, so I'm not going to try to even give you a feel for why this is true. I hope you don't mind. If you like, you could look in the book about the chain rule, but even in our textbook, they do not try to give a full explanation about why the chain rule is true or where the formula comes from, just because it's a little too technical to get into. But anyway, I hope you won't mind if I just tell you the chain rule. It's not a complicated formula to use. It's complicated to explain exactly why it's true. But this is the formula in any case. Make sure you get the primes in the right spots on the right side there. It is f prime of g of x times g prime of x. All right? This is the formula for the chain rule. And just like the product rule and the quotient rule, you need to memorize this eventually, although I don't think you're going to have to just like sit down and memorize it, because we're going to be using this a lot. And also, when I remember the chain rule, I actually don't really have this formula memorized per se, but I sort of remember more of a slogan form of this. So the way that I think about this is, what you see first there is the derivative of the outside with the same inside. What I mean by that is, when you start here, you have the outside part, which is the f, and the inside part, which is the g. And you'll see this first thing here represents taking the derivative on the outside, but leaving the inside like it was, all right? So this is the derivative of the outside with the same thing on the inside, and then separately times the derivative of the inside. So this part is derivative of the inside. All right? And you multiply those two things together. This is the chain rule. And this is really this is how I have the chain rule memorized. I don't really think in terms of these f's and the g's. I just think of it as you do the derivative on the outside, keeping the same thing on the inside, and then separately you multiply times the derivative of the inside. This is the chain rule. All right. Let's just try some examples. Sometimes it's a little tricky to identify which part is inside and which part is outside, but usually it's not so hard. How about can we do that one that I said at the beginning? X squared plus 1 all to the 100th power. So let's try it. Derivative of x squared plus 1 all to the power 100. And remember what I said before, so you have to look at this and first decide for yourself, what is the inside and what is the outside? The inside here is x squared plus 1. And the outside is the 100th power. All right? This is usually not hard to tell. I mean, you can see those parentheses, and obviously something's inside of them and something's outside. So in this case, the inside is x squared plus 1, and the outside is the 100th power. So when I do the chain rule, remember the little words, the voids. You begin with the derivative of the outside, but keeping the same stuff on the inside. The outside is the 100th power. So when I do the derivative of the 100th power, you just do like usual with a power. The 100 comes down to the front as a coefficient, and then you decrease the power by 1 to make it 99. What goes inside the parentheses? I said so in the formula here. It's the derivative of the outside with the same thing on the inside. So you put the same thing on the inside. Do not also take the derivative of the inside. You may be tempted to also take the derivative on the inside, but that's not how the chain rule works. You do the derivative on the outside, leaving the same thing on the inside, and then separately, I go times, remember there's a times here, right? Times, separately, the derivative of the inside. So now over here, I'm going to do the derivative of the inside. What is the derivative of the inside? Someone want to shout it out?
2x.
2x, yeah. Great. So this is my answer. This is how we do the chain rule. It's the derivative of the outside with the same thing on the inside times the derivative of the inside. All right? And as usual, you could try to simplify that if you want to. Like, these are all multiplied, so you could, if you like, combine the 100 and the 2, make it 200. I don't care about that. Unless you have some good reason, I would expect you to just leave it unsimplified like that. All right. Great. Let's try a few more. That was a fairly simple example. I got another simple one, and then some that are a little more taxing. How about 3x squared plus 7x all to the 5? This one is very similar. It has the same structure. We do the derivative of the outside part first. The outside part is the 5th power, right? So I'm going to do the derivative of the outside part, the 5th power. The 5 comes down here with the same thing on the inside. And then you decrease the power by 1 to make it 4. So that much is the derivative of the outside with the same thing on the inside. And then I say plus, not plus, times the derivative of the inside. Just so you can see the cracked screen. Times the derivative of the inside, which is whatever that is, 6x plus 7, right? That's the derivative of the inside. And I hope you put those parentheses around 6x plus 7. It matters. Because in theory, if you were going to simplify this, you would have to distribute across that. If you left out the parentheses, it means something different. All right. Yes?
So you left out the parentheses at the top.
Yes, that's true. It's because this one, the reason the parentheses here are important is because there's an addition inside.
Oh, okay.
It's because of the way this is going to distribute with the other stuff. And that's because of the plus. Here, there's no plus in there, so it doesn't matter.
Okay.
So it's not, it's not wrong to put them there, but it has the same meaning either way. Great. All right, let's try some other ones. I got one more that's more or less the same, and then one that is actually considerably more difficult. This one is interesting because of the square root sign. So let's talk about the square root sign. Again, is a situation where you're going to use the chain rule because it has an inside and an outside. In this case, the inside is 2x to the 5 plus x, and the outside is the square root. But we are going to handle the square root in exactly the same way that we always handle the square root, which is to say we rewrite it as a 1/2 power. So before doing anything, this is like a preliminary step. I am going to write this using a 1/2 power instead of a square root sign. Basically, writing with a radical sign is basically never helpful in this class. You should always immediately change it into a square root sign. All right? But this is not the answer. I didn't do any derivatives yet. I'm just rewriting the same thing. So starting from here now, we're going to do the chain rule. Now this, again, it has basically the same format from before. Although there is this extra 4 in the front. You may be concerned about what am I supposed to do with this? And my reply is, don't be concerned. This is just a constant coefficient. When you're doing the derivative, if you have a constant out front, it's just going to stay like a constant out front. So this constant coefficient, let me just indicate this. Constant, if it's a constant, coefficient stays as is in the answer. Meaning you don't have to do anything special with that. It's not going to disappear. It's just going to stay where it is. So I do the derivative on the outside, which is the 1/2 power, comes down and multiplies onto the 4. So this is now 4 times 1/2, 2x to the 5 plus x. You leave the same thing on the inside. And then I decrease the power by 1. Everybody knows 1/2 minus 1 is negative 1/2. So it's like so. That was the first part of the chain rule. That's the derivative of the outside with the same thing on the inside. And then I go times the derivative of the inside. Someone want to shout it out? (10x to the 4 plus 1). Excellent. And I could hear the parentheses in his voice when he said that. That stuff has got to be all together because it's two things added together. All right, that's how we do it. Again, I will say, if you want to, you can try to simplify that, although I don't think it's necessary in my opinion. Pretty much the only thing you can do is this, multiply 4 times 1/2 if you want, and make that a 2. Otherwise, you can't really do much of anything with that. All right, excellent. One more, and then I have some for you all to try. So this one is really sort of significantly different. How about that? X times x squared plus 1 to the 10. What's different about this, something you see here which you didn't see in any of the others, is actually this is two things multiplied together. There's this part and this part. All right? This was not the case in any of the other examples. Now in this one I had the 4 out front. That was a constant in front though, which doesn't really affect anything. If you have this, it's not a constant, it involves the variables. This actually has a big effect. What that means is this is a product, which means we need to do the product rule because I have a product of two things. The first thing is x, the second thing is that stuff. So we need to do the product rule. And I hope you all remember the product rule. It is the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. All right, that's the product rule from last time. That's what we got to do here. And at a certain point, we're going to have to take the derivative of the second part. And when that time happens, we have to use the chain rule because this second part actually looks similar to the ones we've been doing already today. All right, so it's a product rule, and inside of that, as a piece of it, will be the chain rule. That's what's going to happen. So I'm going to write out my result of the product rule. It is the first thing, which is x, that's the first thing, times the derivative of the second thing. And when I do the derivative of the second thing, this is when I'm going to have to do the chain rule. So I do the outside first, 10 x squared plus 1 to the 9. That's the derivative of the outside. And then times the derivative of the inside, which is 2x. So all of that was just the derivative of the second. All right? This is a chain rule as a little piece of a larger product rule. All right? And then, continuing the product rule, I go plus second times the derivative of the first. So the second thing, I just write the second thing as is, times the derivative of the first. So that's the second. Can someone say, what's the derivative of the first part? The first part of the product is here.
1.
1, yeah. The first part is just x, so the derivative of x is 1. So this is 1 here. This is derivative of the first part. All right? And that's my answer. Fairly complicated, I would say, but this is a product rule, which has a chain rule inside of it as a little piece. When I did the derivative of the second part, that was the chain rule. All right? This is the kind of thing which you will expect to see. You know, most of these problems, like a problem just using the product rule or just using the chain rule, is typically fairly simple. If you look on our big checklist, you will see, I believe number 11 is the product rule, number 12 is the quotient rule, number 13 is the chain rule. Individually, those things are not so difficult. It becomes tricky when they are combined together in weird ways. And so I made a special one for that. Number 14, I believe, is called derivatives misc. That means some kind of weird combination of the product, quotient, and chain rules, which I will leave to you to decide which one it is. You know, these questions are always labeled, so you always kind of know what the question is supposed to be about, even if you have no idea how to answer it. But that one, you're going to have to decide for yourself what to do. So this would be an example of one of those kinds of problems. A weird function, which is some kind of combination of products or quotients or chain rules, and you have to figure it out and work it out. All right, I got some of these for you all to try. See what you think of these here. The first two are just simple sort of direct chain rule, and then the second two have some weird combined stuff going on. All right. Can we say just before we get going here, what are you going to do? This here, this is a cube root. This is not 3 times the square root. It's a cube root. Anybody recall, how do you handle a cube root? Everybody knows the square root is the same as a 1/2 power. What about the cube root? Anyone remember this perhaps from your youth? Yeah?
1/3.
Yeah, the cube root is a 1/3 power. So when you're doing this one, your first step should be to rewrite this using a 1/3 power instead of that root sign. All right, see what you think. I'll come around and see how you're doing. Feel free to chat with your friends. Everyone can still see, right? Doing okay? Nice. Okay.
But it's something like this. It's in there somewhere.
Doing all right?
I just wrote regular.
Remember when you do the, you're doing the derivative of the sheet now? Well, it's usually the same stuff like that. It's not actually.
You get 14 to the other.
Yeah, actually, that's what we do with this one. So, what I just said, you don't do the okay? Okay, so the cube root, I said before, the cube root is the 1/3 so it's really, yeah, and then the exponent is different. Actually, it looks like you forgot, there should be an here. Minus something.
First times the derivative of second.
Yeah, so this one is just basically like reverse, like this one. So I think just put this one as first here.
Yeah.
You can start side four.
It used to be 1/3, and you increase it by 1. Alright. That's good. Yes.
So do you do the product for the chain rule first?
Overall, this is a product.
Yeah. But then, wouldn't this be the chain rule first or no?
No, because in the product, you begin with the first thing as is.
Yeah.
Times the
So
derivative.
you can take the derivative of the first thing.
Yeah, I know that.
Okay, so I do the product rule.
They do the chain rule.
X squared plus 1. Plus, or times 2. Yeah. Okay, opposite way, okay.
Yeah.
Oh, I agree.
And then decrease it by 1.
Was it 2? Or not? No. Okay. Just look, it's X.
Uh-huh.
All that stuff.
This is right.
No, like you have to do the whole chain rule inside. It's probably
I would think that times
This is asking us this is not where you're trying to use it, and then you increase it by 1.
so it's all comes
No, because it's a 1/3.
Oh,
Well, I'm giving you that. So just imagine. This is cube root, which is but that's not the answer.
So this is original chain rule.
Yeah. Yeah, when you multiply it down.
So like that number, yeah, it's just no.
Well,
Just got the end of it.
yeah.
Okay, but like, so then inside the parentheses.
Well, it's the product rule, but like when you do the derivative, the first one, you're just doing whatever.
And then when you actually do the chain.
It's in the product rule for you.
Maybe times 2. Times 2.
No.
Yes.
How is it 2?
Because 2 is the derivative.
Oh, 2 to the 4.
Well, you have to treat it as a product.
Huh?
No, this is already missing this. No, it's in the first one. I'm printing it out.
Yeah, that's, those ingredients are part of the answer, but that's not. What you're doing, you have 2 parts, and you just do the derivative of each part. But you can't do that when you have 2 things multiplied. You do the product. So you won't go do the first thing times derivative, the second thing is plus the second thing times the first. Now, you you just told me what the first thing is for the second one.
I should see that.
Doing okay?
Yeah, it's on the third one now. It's not gonna get.
This one.
That's not gonna.
This, when you do that, you should decrease the power by 1.
You're getting.
Doing okay?
I have the negatives.
Yeah, you do 1/3 the minus.
All over the bottom square.
Right.
Really nice for subtracting fractions. One is like 3/3, so it's 1/3 minus 3/3. How's it going?
I don't know. I'm not good with it.
This one is not quite right. You have 2 things here. Just like you just did.
One minus 3 was it? It's true.
You have 2 things multiplied together. You don't just make sure this is the product.
I'm fucking
Yeah, she's jumping as
Sorry, Pastor, we gotta change his note. I already tried. This one, this one.
Oh, it's, is it?
Never made it.
Yeah, it was basically.
Look up next.
I do the third one.
Sorry, yeah.
Do the third one. I'm almost done.
You do the product over.
Where'd you get number 3?
That's what we're trying to figure out right now.
All right, can we go over these? I know not everybody's finished yet, but I want to get on with it. People seem pretty good with the first one. So this one is just a very straightforward chain rule thing. You bring the 4 down to the front. Same thing inside. Then decrease the power by 1, it becomes 3. And then, so that's the derivative of the outside with the same thing on the inside. Can you guys all still see when the window's open?
Yeah.
Yeah? All right. Or you can see that one? Okay. I like the window being open, but if you can't see, then I can close it. And now separately, times the derivative of the inside, which is going to be 6x plus 7. So pretty much everybody got that one as I was coming around. The next one is similar, but it has this cube root. So before taking the derivative, this step I'm just rewriting the original thing. It is x to the 5 minus 7x squared to the 1/3. That's what cube root means. It means 1/3 power. And so I do the chain rule on that. The 1/3 comes down and multiplies onto the 6. Becomes 6 times 1/3. And then this business, x to the 5 minus 7x squared. And now I change the exponent by subtracting 1. What is 1/3 minus 1? It is negative 2/3. That's because 1/3 minus 1 is like 1/3 minus 3/3, which is negative 2/3. This is easy to mess up if you haven't added fractions in a while, but ask your 7th grader sister, and she will tell you how to do it. And then the derivative of the inside, which is 5x to the 4 minus 14x. So I hope that's what you got. Any questions about that one? Okay, those two I consider the easier ones. The second one was a little weird because of the 1/3 power. Whoa. Let's try this one. So this one, I saw a fair number of people who just figured, who just sort of did, well, can't I just do the derivative of the first one and then also do the derivative of the second one? The answer is no, my friend. You need to do the product rule because this is a product right there. When you have two things multiplied together, taking the derivative, you must do the product rule. So I do the first thing like it is, like so, times the derivative of the second thing, which is 2, and then plus the second thing like it is, 7, times the derivative of the first thing, and now is when you're going to do the chain rule. The derivative of the first part requires the chain rule. So I get 4 down front, x squared plus 1, and then to the third, and then times the derivative of the inside is 2x. This is how we do it. That's different from if you just took the derivative of the first one and also the derivative of the second one. That's not good enough. You got to do the product rule. Any questions about that one? I hope we got something like that. And then the last one is kind of similar, but it's a quotient rule. So again, I will say, do not just take the derivative on the top and also take the derivative on the bottom. This will give you the wrong answer. You must do the quotient rule, and I hope you remember the quotient rule. It was that ho d high minus high d ho over ho ho thing. It's the bottom times derivative of the top minus the top times derivative of the bottom, all over the bottom squared. So that looks like, what I say first was the bottom, just like it is. That's the bottom times derivative of the top. The top is x, so the derivative of the top is 1, minus the top, which is x, times derivative of the bottom. And now we do the chain rule, because the bottom is a composition, it requires the chain rule. I go 2 in the front, and then the same stuff, and then decrease the power to a 1. And then times the derivative of the inside of the bottom is 4x plus 7. Like that. This is almost done. That's, remember, I'm doing the quotient rule here. So that was the bottom times derivative of the top minus the top times derivative of the bottom. And then I have to go all of this over the bottom squared, which is 2x squared plus 7x squared, like so. The end. That's a complicated one, in my opinion. All right. Any more thoughts about this? You'll have some more practice with these on the homeworks, but these are the chain rule. In my opinion, just the chain rule by itself is not so tricky, but when it's combined with these other things, it can be quite a bit more confusing. All right? All right, let's talk about the next thing then. We got plenty of time for another thing. That was the chain rule. The next thing you see on the list is about exponential functions. Our main goal in all of these topics is to sort of gradually broaden the set of functions which you know how to take the derivative of. We started with just polynomials, which is pretty restrictive. But then we talked about the product rule, the quotient rule, so you can do any products or quotients of polynomials. And the chain rule means you can put things inside of other things. Another completely different type of function, though, is called exponential functions. And these are ones which I'm sure you've heard of, like you've done something with these in high school probably, like 2 to the power x, or 10 to the power x squared plus 7x plus 1, right? These are called exponential functions. And these are ones where the variable is inside the exponent. That's what makes it an exponential function. The variable is in the exponent. All right, that's called an exponential function. This is different, not something like x squared. I mean, it has an exponent there. I see an exponent, but that's not called an exponential function. That's called a polynomial or whatever. This is exponential function means the variable is in the exponent. All right, and when you have an exponential function, the rules for the derivative are totally different from the power rule. The power rule is what you use for functions that look like this, where the variable is downstairs and there's a constant in the exponent. But if it's one of these guys, they are very different functions and they have different rules that go with them. So that's what I want to talk about for the remainder of today. Exponential functions and how you take their derivatives. I thought maybe I would start by saying exponential functions are super important in the real world. They come up all the time in biology, especially. Things which are growing, like population grows exponentially. All kinds of things in the real world grow exponentially. Even some like artificial things, like if you look at people's sort of like, as you may know, I'm sort of a Z-lister YouTube person on the side. And if you look at like a graph of my subscribers over time, it looks something like this. It has this kind of exponential curve to it. It's not a straight line. And why is that the way that YouTube subscribers works? It's because at the beginning, I was posting videos on YouTube for many years before anybody cared. And now, like, almost nobody cares. It used to be actually nobody cared. And why did I stay at no subscribers, or essentially no subscribers, for so long? It's because on YouTube, the way to get more subscribers is if you are suggested to other people. And the way to get suggested is if you have a lot of subscribers. Like, there's no easy way for somebody with no clout to gain clout. But once you have some amount of clout, it's a lot easier to get subscribers over time, right? For this reason, things like YouTube channels or like all kinds of social media following tend to grow exponentially. If you're just an ordinary person with social media, it's like your friends follow you and that's it. But if you're some kind of celebrity, you gradually grow in following, and the more followers you have, the more followers you can get, and so you end up growing exponentially. Anyway, all of these things, if you want to appropriately model them in the real world, you use exponential functions. So let's talk about that. I actually had, just to get us warmed up, I had a real sort of a made up real world example. Let's say there's a pandemic. You know how that is. Let's say that on day 0, we have 50,000 people are infected. I'll just say 50, but this is in thousands, all right? And let's say the pandemic is spreading. It grows by 1% each day. All right? It doesn't sound like I'm saying anything exponential, but actually the proper way to represent this as a function is using an exponential function. This cannot be represented with an ordinary polynomial or something like that. And it's because I said it grows by 1% each day, right? Let's see if I can try to come up with a formula for this. So let's write a formula for the number infected on day t, right? F of t equals something or other, the number of people infected on day t. So, for example, if I wanted to, let's just, I don't know what this is going to look like yet. I will just try and do some simple examples. F of 0, this would be the number of people infected on day 0, which I said already is 50, meaning 50,000, all right? What about on day 1? Well, it says the rule is this grows by 1% each day. I suppose you might want to use a calculator to do this, but can anyone suggest how would you figure this out if you needed to say how many people will be infected on the first day if it grows by 1%? You don't have to give me the answer, but because you might want to use a calculator. How would you figure that out if you had to? Grows by 1%. Yeah? Multiply by 1.01. I like this idea a lot. This is exactly what I was going to say. 50 times 1.01. Why do you say 1.01?
Because it's 1 plus the 1%.
Yeah, the idea is you had 50 on day 0. On the next day, you still got that original 50, but it's going to be increased by 1 more percent. Another way to think that through would be, it's kind of like multiplying by 101%, which is what that number is, right? 1.01 is like 101%. All right, so that, whatever that is, actually this is not so hard to do without a calculator. This would be 50.5, which is 50,500 people, if we're doing this in thousands. Oh, what about the next day? F of 2. This would be the same thing from the first day, but then you go times 1.01 again, right? Because whatever it grew to in the first day, it will grow again in the second day, and the way you sort of work out the growth in the second day is again by multiplying by 101%, which is 1.01. Now this, I don't know how to do this without my calculator, but if I were doing this, just to simplify a little bit, I could write it that way, right? 1.01 squared. because that's what it is, 1.01. What about the next day, f of 3? This is 50 times 1.01 times 1.01 times another 1.01. Each day, it grows again by 1%, which would be 50. Again, I don't know what this is without using my calculator, but it's like that, right? Anybody see the pattern here? You don't have to be a genius to see the pattern here. It's f of t is 50 times 1.01 to the power t, right? This is exponential growth. Now, 1% is not very fast growth, but it's still exponential growth. 1.01 to the power t. All right? This is how things work in the real world. Okay, that was just a little example to show how exponential functions can appear in the real world. What about if I wanted to take the derivative of such a thing? So how about the derivative of an exponential function? Like, generally speaking, these things look like f of x equals something like this, a to the power x. The variable is inside the exponent, where the a is just some number. And the terminology we use here, the number down there is called the base. And the x, of course, is called the exponent. But f of x equals a to the x. You know, like I'm thinking about something like 2 to the x, or 10 to the x, or like the example we just talked about, 1.01 to the x, right? Those are all different values of a. The a could be 2 or 10, or it could be 1.01. So I would like to know the derivative of an exponential function. It turns out there's a formula for this, and it's not very difficult to work with. I wanted to say a few words about where this formula comes from. So what if I just start with a to the x? I thought it might be fun to talk about this one in terms of graphs. I don't know if you ever tried this, but you can graph a function like a to the x on your calculator. It looks like this. I hope you'll believe me. It looks like this. It starts off sort of not growing much at all, but eventually it grows super fast over here. I didn't go far enough to see the super fast growth, but this is what the graph of a to the x looks like. And it's, of course, the graph is slightly different for different values of a. If you change the a, I will say bigger a is steeper. So if you're doing something like 2 to the x might look like that, but 3 to the x would look like that, but it's a little steeper. 4 to the x would be a little steeper again, and so on. And these functions, they always go through here at 1. That's because anything to the power 0 is 1. So if you plug x equals 0 into this, you get a to the power 0, which is 1. So these functions, they all basically look like this. They go through 1 here, and they have some varying steepness based on what the precise value of a is. All right. Now, what about the derivative of that? So if I were to try to do this graphically, first of all, like on the, we had a test question about this. I draw the graph of a function, you draw the graph of the derivative. First, you would look for places where the derivative is 0. And actually, looking on here, I see no points like that. That would be like the bottom of a valley type situation, which doesn't happen here. In fact, I would say the derivatives here are always positive, because it's always going up as you move to the right. Although on the left side of the picture, it's not going up all that much. I would say the derivatives, if I were to do my little p's, it's always positive and becoming increasingly big positive as you move to the right. Okay, so if I want to draw the derivative, which believe me, I do. If I want to draw the derivative, what it's going to look like is always positive and increasingly so as I go left to right. So on the left side, it's going to be positive, that is up here, but pretty small, like close to the x-axis. And then as I go to the right, it's always going to be positive, but even bigger, bigger, bigger as I go to the right. It looks something like this. Right? Positive, but only a little bit over here. And then going to the right, increasingly more and more positive. This is the derivative of a to the x. Anybody want to notice any similarities or differences between these two curves? I would say they look the same. This is the similarity that I hope you will notice. They are looking the same to me. Now, I just drew this by hand, so it's not a guarantee that they are actually the same, but at least they have a very similar shape. It turns out, and here I'm going to get to the formula that everybody's waiting for, the derivative of a to the x has the same shape, at least, as just plain a to the x. The only difference is, it turns out, and this you can't tell by looking at my pictures, but it turns out the steepness from one to the other is slightly different. So the only difference is this one is the same as this, but it's been multiplied by a constant to make it either more steep or less steep, depending on what the a is. And so it has the same shape as a to the x. The only difference is it's just multiplied by a constant to change the steepness a little bit. And that constant is, this is maybe a little confusing if you've never seen this before, the constant is this, ln of a. This is the natural logarithm of a. This is something that we are going to talk in detail about in the coming weeks. We're going to talk a lot about logarithms. That may be something you already know about, which is great. For now, though, I'm just going to treat this like the ln is a button on your calculator. And if you want to know what this number is, you can just type into your calculator and get that constant. So the constant, like this a, it could be 2 to the x or 3 to the x or something. The constant multiple is always the natural log of whatever the a is, 2 or 3 or whatever. So the true formula, I just wrote it in words. I'll write it as a more kind of math-looking thing. It's this. This is the formula for the derivative of an exponential function. The derivative of an exponential function is the same function again, but then times this extra constant, natural log of a. All right? And that extra constant, that ln thing, is a thing that you can do on your calculator. You essentially can never do the natural log like in your head or by hand. It's something that you need to use some kind of computer assistance for. The only thing I'm going to say about ln for now, we're going to talk in a lot more detail about this later, but I will just say ln is a weird sort of calculator function. By that I mean you can't do this by hand in any way. Calculator function. The only thing that you should know at this point about the natural log is there is one special number for which the natural log of that number equals 1. And because of that, this special number is super useful in calculus. There's a number called e, which satisfies, this is the whole point of this number e. The natural log of e equals 1. This, you can check this on your calculator. E is kind of like pi in that it's like a weird irrational number where the digits never repeat. E is something like 2.71, I believe, is how it begins. There's some people memorize the digits of e. I am not those people. I'm not that guy who knows a lot of digits of e. All right. But anyway, all you have to know is that the natural log of e equals 1. And what that means is, if you're doing this, but you are using that special number e for your function, then this formula here is a little easier. So e is very nice when used as a base. This number e, compared with pi, actually e is very new historically speaking. Pi was discovered like thousands of years ago, but e was only discovered in like the 1600s, I believe, when people started doing calculus. Before that, nobody really cared about e, but it's super nice when you use it as a base in calculus, because this formula here, if I write it down using e as my base, it will say, sorry, I had to scroll, e to the x times the natural log of e, right? I'm just plugging into that formula up there, but using e instead of a. But the nice thing about e is that the natural log of e equals 1. And so this turns out to just equal e to the x. So this this you should memorize also. So I'm going to write them both sort of together here. The derivative of, I'll write the e one first. This is like as good a formula as you can imagine. The derivative of e to the x is just e to the x. This is everybody's favorite calculus formula for that reason. The derivative is equal to itself. The other one, if it's not e, if it's like 2 to the x or 10 to the x or something, you have to use this other one, which is not so complicated, but it involves this extra little part. Right? So these are the formulas for derivative of an exponential function. Generally speaking, this is, I don't know if you're feeling this yet, but like when you see a problem on the homework or on the test about exponential functions, you hope deep down inside that it's an e, because the e has an easier formula. If I want to mess with you a little bit, I'll make it some other number, not e. And then it's slightly harder. It's not really hard anyway, but the e works nicer. All right? Yes?
Can you scroll up just a little bit?
Yeah, sorry. E is very nice when used as a base. More than that?
Yeah, that's good.
Yeah. It is very nice when used as a base. Okay, let's see if we can get into this. Let's just do some examples, all right? So, examples that are basically just plug it in. What's the derivative of 2 to the power x? So you, first of all, look at the number and decide for yourself, is it e or not? It's not. It's 2. 2 is different from e. So I have to use the second formula there with the a in it. And using the second formula, I get this. 2 to the x times the natural log of a. All right? That's this formula here using 2 instead of a. That's all there is to it. Can I just say on a little sidebar, don't you dare do x times 2 to the x minus 1. Isn't that foolish? This is the power rule. You might look at that and say, oh yeah, I know how to do that. I just bring the exponent down to the front and then decrease by 1. You do not do that when it's an exponential function. That is appropriate to do when it's a polynomial-like thing, where the x is downstairs and you have a constant up there. But when it's x inside the exponent, it's a completely different situation, and you cannot use that power rule anymore. So don't do that. All right, let's just look at, what about if it was 10 to the x? It's just 10 to the x ln of 10. Why? I wrote ln a here. Sorry, this right there, I was supposed to be plugging in a equals 2. I left it as a a. It should be 2 here. I suppose it would. I meant 2. Sorry about that. All right. If it's a 10, you do 10. It's just whatever that number is. You use that in place of a in this formula. And if you're lucky, it's a e. And if it's a e, then you just get e to the x again. And you don't have to do no extra funny business with the natural log of whatever. All right? That's why we love e so much in calculus. Okay? Now, these, again, like before I said, these by themselves are not terribly interesting. They become interesting when you have things combined with other things. So this exponential rule is more interesting when it is combined with other stuff. So for example, let's try something like 10 to the x squared minus 7x plus 2. The derivative of this. What am I going to do with this? This is a chain rule. I don't know if it looks like that to you, but this is a chain rule because it's one thing which is stuck inside of another thing. And the inside part is the polynomial up there in the exponent, and the outside part is 10 to some power, right? So the outside part is an exponential function with base 10, and the inside part is that stuff which is inside of the exponent. All right, so we're going to do the chain rule. I hope you still remember the chain rule. It is You do the derivative of the outside part with the same thing on the inside, and then times the derivative of the inside part. So the derivative here, I'm doing the chain rule. Derivative of the outside part first. The outside part is 10 to some power, which means I use the a to the x rule because it's not an e. I will just copy it here to remind us. A to the x ln a. So I'm using this rule here with 10 for a and the thing on the inside instead of x. So it looks like 10 to the same thing on the inside times ln of 10. So all of this is the derivative of the outside with the same stuff on the inside. Right? I used this a to the x formula here, where instead of a I have 10, and instead of x I have that more complicated stuff on the inside. All right? And then times derivative of the inside, which is 2x minus 7. So this is the derivative of that thing. This is the chain rule when used with the exponential function. Any thoughts about that one? These can be a little confusing. I got just a few more here. How about derivative of 6e to the 8x squared? This one is going to be a little nicer because of the e rather than a 10 or something like that. I will refresh our memory. Derivative of e to the x is just e to the x. All right? But again, I have to do the chain rule here because I have a complicated thing on the inside. So I begin by doing the derivative of the outside part, which is just the e. Now I have a 6 at the beginning, but remember what I always say, a constant coefficient in front just stays like a constant coefficient in the answer. So this is still going to be a 6. But then I have now the derivative of this e to the 8x squared part. I do the derivative of the e part first, which is the same again, because that's what the derivative of e to the x is, e to the x. So this is going to be e to the 8x squared again. That was the derivative of the outside, which was the e part. And then times the derivative of the inside. The inside is 8x squared, and so the derivative of the inside is 16x. This is the chain rule as part of an exponential function. All right. I got 2 more examples, and I think we can go. I had some for you to try, but we can start off at the beginning next time with that. Let's just try a couple more. How about, this is somewhat weird looking, x times e to the x. It's an e, which is nice. We don't have to do any extra ln business. But what about x in the front? How do we handle x times e to the x? This is 2 things multiplied together, so we must use the product rule. So I got this part and this part, right? And I have to do the product rule now. So it's going to be the first thing like it is, x times the derivative of the second part. The second part is e to the x. What is the derivative of e to the x? Say it proud. It is e to the x. It's the same thing. Okay, that's the first part of the product rule, right? That's the first thing. This is derivative of the second thing. And then plus the second thing like it is, which is e to the x, times the derivative of the first thing, which is just 1. All right. In this case, in the answer, there's 2 different e to the x's. One is the second part originally, and one is the derivative of the second part, but they're both equal to e to the x. All right. And for one last thing, I thought maybe we should just, can we revisit my real life word problem before? It said f of t equals 50 times 1.01 to the power t. All right. Can we do the derivative here? And I would also, just for practice, let's try to say what is the meaning of the derivative. So if this would make a nice little test question. Find f of, let's do f of 50 and f prime of 50 and say what they mean. All All right. So the one without the prime is easier because you don't have to take the derivative of anything. You would just do f of 50 is, sorry, I meant to say 100. It doesn't matter, but I did these ahead of time on my calculator, so can I change this? Sorry about this. F of 100 is what I wanted to do because I have the numbers for that. F of 100, that means you just plug in 50 times 1.01 to the 100. And this, if you type those numbers into your calculator, I did this and I got 135.24. So what does that mean? Remember, f of t is the number of people infected on day t. So what this means, my interpretation of this would be on day 100, there are 135.24 thousand people. I wrote people with two E's, infected. All right. I said before, all the numbers are to be interpreted as thousands. So that's why I put this, this little k over here. All right. That's the meaning of f of 100. What about f prime of 100? It's different. So f prime of 100. For f prime of 100, first we should find the derivative. So let's find f prime of t in general as a formula, and then plug in 100 for t. First find f prime of t, then plug 100. So what's it going to be? I will remind us, f of t was 50 times 1.01 to the power t. The appropriate rule to use in this case is this one with the a, because it's not a e there. The base of this exponential function is 1.01. Anyway, we're going to get a to the x times ln of a. So this is going to be 50 stays like it is because it's a constant coefficient. And then the derivative, sorry, I forgot to write, f prime of t, I'm taking the derivative now. The constant coefficient stays like it is. And then the exponential part, you do this formula, a to the power x times natural log of a, where a is 1.01, and I'm using t for x. So this will say 1.01 to the t times natural log 1.01. That's plugging into the derivative exponential formula. All right, and this log of 1.01 is a constant. If you do that on your calculator, it's 0.00995. So actually, if you multiply these constants, you can simplify. This is 0.4975 times 1.01 to the power t. I did this on my calculator ahead of time. All right, this is the derivative, f prime of t. Okay, remember our actual goal, it still says this at the top here, for f prime of 100. First find f prime of t, then plug in 100. So now I'm going to plug in 100. So f prime of 100 is 0.4975 times 1.01 to the power 100. And this I did on my calculator, 1.34. What does that mean? Anybody want to try and say what the meaning of this is? The function f of t is about how many people are infected. What do you say?
Is the rate that people are getting infected at?
Yeah, so this number in particular, it represents the rate at which new infections are occurring, which is what he said. If I wanted to be very specific about it, to say all these numbers here, if you're going to write this in a sentence, your sentence should probably include the number 100 and also the number 1.34. So what this means is, what the 100 means is on day 100, the infection or whatever is growing by that many per day. So the number of infections is growing by 1.34 thousand per day. There you go. This is the meaning of that. Which, of course, this is useful information. Like in real life, you would actually want to be able to do this to figure that out. All right. I think that'll do it for today. We do have homework due tonight. Let me know if you have questions about it. I would be happy to chat. Otherwise, I'll see you Friday.